Okay, so having talked about these gimbal acceleration loops that we have to create to track a gimbal rate, let's talk a little bit about the code flow that we'll be using. So generally, let me just write a time loop, This is from time is equal to t0 and to tf, right? And we're going to do this. Let's call it delta t increments. You have this primary simulation loop. I'm starting at 0. I'm going to run for 10 minutes, and I'm going to update every 1/10 of a second. That's what you want to do, right? So jumping to the bottom, somewhere you basically, you have your state space, and you do your integration, like probably at least a Runge-Kutta fourth order. If you want to use MATLAB and got OD45, fine. A fixed time step fourth order historically works reasonably well, But you have your states, and you have to propagate them to the next time step. So we got our state vector plus, all the RK stuff that you do. You put them in there. So this gives you at the bottom the new things. If we're doing MRPs, what do you have to do after you integrate? Yeah, you have to check. You have to check the elements of your state vector. Does sigma norm become less than or equal to 1, essentially, right? So don't forget, that's where that switching goes. Do not put the switching inside your RK, because you do 4 different RK4 evaluations, and if one of them gives you 179, the other one gives you minus 179, and you're going to average it, you get 0. You actually get a wrong answer if you try to be extra careful and do switching inside the RK. Nothing bad happens to MRPs if you punch through that unit sphere. So just let the RK do what it does. That's the beauty of these things. You don't have to make it overly complicated. Just integrate forward. But if your answer is 1.001 in norm, you go, okay, well, let's just switch it. We'll keep track of the minus 179 instead of plus 179, right? So that's where that one should go. Good. At the beginning, you also have to initialize everything, of course, right? So before you enter the time loop, what's your initial gimbal angle? What's your initial attitude? What's your initial body rates? Wheel speeds that you have initially, especially now that we're doing variable speed stuff. And then we go in there. So let's see. One of the things you have to compute is LR, right? And that might be then your minus K sigma B relative to R minus P omega B relative to R plus all these other terms, right? We had all that stuff that we would compute for the outer control loop. That was kind of the right-hand side. This is the required torque that must act on the body. If that acts on the body, then for the steering laws, we have negative LR that maps onto these wheel accelerations and gimbal rates that we have. Did you compute this? So do I compute this every time step, Ricardo? Yes? You seem uncertain. You're answering in a questioning yes. Yes. You could, and there's different ways we can do it, right? We may not be running our outer loop though at 10 hertz, but again, in the code sometimes there's nothing wrong with 10 hertz. Just make sure the spacecraft performance, the closed loop performance doesn't push 10 hertz. It should be going way slower. And that's, how do we control how fast the spacecraft reorients in the end? Yeah, it's these gains that you pick. That really controls it. The update period must be fast enough that if I have a 60 seconds, it takes 60 seconds to settle from here to over here, you probably shouldn't be updating the control every 45 seconds. That's just going to give you rubbish, right? But if you update it every second, you might be perfectly fine. And if 1 second is fine, then so is 1/10 of a second, right? A little bit overkill. So sometimes we often don't do it at the fastest thing just because it's more effort on your flight computer, right? It has to now update. You have a lot of other evaluations. They have to happen at a certain time. Communication packages have to arrive. You have to process it, and then you get your time slot. I've got 20 milliseconds to compute these answers. And if it's not as busy, you can use the processor for other stuff. So you don't hate to overdo that. But in your sim, you're welcome to start. It's perfectly fine to start like this. Just make sure you pick gains that don't slap you left in 0.01 microseconds, because it will be nasty. Anthony.
So if your like numerical instabilities in your integration are not very small at like 1 hertz running, but your response is like over 60 seconds, like does that just fall into you have to balance those two things?
Yeah, in the essence, right. So I mean, you have always integration errors, but with 16 digits of accuracy, you're not going to be anywhere near those issues. Those integration errors will be really small. And if this control was supposed to put you there, you're also doing a digital implementation. All of our guarantees assume a continuous system. And now we have a discrete updated system. So in here, we're updating every 0.1 seconds if that's a 10 hertz thing, right? And that's not exactly what our earlier stuff did. That was a continuous. So your errors won't decay to 0, but they should get small. And you want to see just how small. Is that good enough? Are you within 1/10 of a second? Do you want to be within 100th of a second? That's going to dictate a little bit how much, how fast, how subtle, to get those little nuances just right. Make sense? Okay, so we do this. So sometimes people get overly complicated at the beginning. But then with LR, right, we have this Q matrix times eta dot equal to minus LR. And eta was big omega and gamma, I believe, right? So from this, we find eta dot, which will tell us the wheel's accelerations and that. So given this, we find now our wheel accelerations and we find our motor torques. Then given this, we map it onto motor torques with your steering laws and the gimbal, right? And there's different ways you can play with that. And there again, inside those, there are gains that you have to pick. For servo, right? These gains, if this will settle, you have gains that make the big spacecraft settle within, I don't know, 30, 40 seconds half-life or something, to slowly converge. How fast do you think you want to pick your gains to make your servos converge? Order magnitude-ish faster. So probably instead of 30, maybe within 3 seconds-ish, you should be close. You don't have to hit that speed within a microsecond, but within a few seconds, yeah, because otherwise our separation principle doesn't hold. We are assuming in our steering laws that we get these rates. And if we don't get them, and there's lots of other dynamics happening, then our stability completely goes out of the window. In fact, we might get an unstable system. All right. So you want to make sure they track reasonably quickly. So that's why also in your homework, you want to first, once you get the dynamics working, then you want to do this, and you just prescribe some sine wave. But don't make it 1,000 hertz sine wave. Make it also something that, hey, these rates, what sine wave should you use then as a reference? Right? What's your desired gimbal rates? You just prescribe those right now because they're not coming from we haven't got this implemented yet. What frequencies would you put in there? Larger ones, right? They have to be the sine periods of the outer loop. So if this control decides to do some kind of a motion, and then you slightly overshoot and come back, and this takes 60 seconds, your sine wave should also be on the order of 60 seconds because you're trying to mimic the actual gimbal rates and wheel acceleration stuff that you would have. Don't go above 1 radians per second. That's usually the max that these CMGs would have. So pick 0.5 or some reasonable number.
Due today.
Really? Let's give me notifications. Okay. Those are reasonable numbers because otherwise most challenges I see is people put in something like just sine of t. That ends up being a really fast rate that spacecraft would be doing, and this makes it a super challenging servo control all of a sudden to track such a fast rate. Okay? So think, these references need to be reasonably small, but then if you have this slow sine wave, it starts out at all of a sudden 0.5 and make it a cosine that starts non-zero, because then you will see the actual rates which starts at 0 converge onto the desired curve, and within a few seconds, you should be reasonably close. It won't track perfectly. We had all kinds of assumptions, but it should track pretty close, hopefully. Get those, play with those gains, get that working. That makes sense? So then we have that. And then once we have this, then we can just integrate onwards. So you can run all this without extra timers and different periods, inner loops. This will work just fine. Again, you're finding the minimum sampling here. That might have been, I could do this every 2 seconds and be fine. But to get the dynamics right, I know I have to integrate every 1/10 of a second. And if this doesn't slow down your simulation a factor of 3 or something crazy, you're just going to go, okay, I just do it every time, as long as I'm at least that fast or faster. If you want to simulate and just set up your code so it's ready, let's say we do time loops for these. You could set up counters, and usually we have integral counters, If I'm updating my system at 10 hertz, 0.1 seconds, I don't pick a control update period of 0.13795 because I'm never going to hit it just right. It will take a long time before I hit it just right. So you could pick 0.2 or 0.3 or 0.5, something that's an integral of that. So could you have this one be updated more often than this one? The purple more often than the blue one? No, right? That outer loop really, if anything, that should be the slowest if you can update. Otherwise, it's weird because you're updating this, but then this doesn't do anything. If this one is slower, this one is really what drives the dynamics through these two things, right? This goes into your x dot is equal to f of x, comma, t, comma, all the control stuff that you had, right? So if you update this more frequently, woohoo, but you're not doing anything. It won't look any different. You're really updating it at this period, all right? So typically we would have this one be slower. Maybe this is every second. This one might be every 0.2 seconds. And then from a dynamics, you might want to go even faster just to kind of get a more realistic thing. And you could update this, maybe every 1.1 seconds or even less, So the dynamic response is extra accurate if you want to play with that, right? Not required. You can just start with everything in the same, but pick a update period that looks reasonable, and you should be able to play with that, When do you get similar results, or when does it start to really go crazy? And don't just start with 1/1,000,000th of a second and go, that worked. It just took 6 hours. That's your problem, all right? You should do better than that. Okay, I hope this is helpful. Because this is basically, you've had this already running for a rigid body. Now we're expanding the equations that get solved, and you're working on that, right? You've had this essentially working earlier with your MRP feedback control that you've already developed. It's just some extra terms that appeared there a little bit with the wheel gyroscopics. But instead of prescribing this as an external torque, we have this coming in as new stuff. It's not that complicated, and now we can put it in, and then so the coding required, once you get your dynamics working to do these things, is actually just a few lines of code. The question is where, how, no typos and sign errors, and what gains. The gains is the big one. João.
I have a question. You mentioned that you have to take the gains from the circle.
Yes.
You mean that when you do that Q inverse, you do the weighted Q inverse, right?
No, actually, so the question was, picking servo gains, are we talking about this inverse here? Because we did a weighted minimum norm. Yeah. Those are other gains that you get to pick and how much you want to use reaction wheel versus CMG. So yes, that's set there. I'm talking about, let's see, the motor torque, the servo equations. Like here, this is for the acceleration. We'd have some feedback gain on how much acceleration you're going to ask for to track the speed that we have. And then if you plug gamma double dot into the gimbal motor torque equation, right, it was UG equal to some inertia times gamma double dot and other stuff. That's what goes in. But the gains come from your servo. And here, same thing. You may have a gain, or you may just do it open loop, no gain. A lot of people do that with reaction wheels. They count on the outer loop to kind of keep the whole thing stable if you're off a little bit. So you could just go from here and say the reaction wheel's spin axis motor torque was equal to spin axis inertia times big omega dot plus some other terms. The body acceleration we typically drop because it's really slow, you know. But that would just give you an open loop version that if you're asking for this, I will give it to you, right? Because here we are getting an acceleration versus gamma dot just gives you a rate. It doesn't give you an acceleration. And we need a gain to say, okay, how do we make this there?
And so that gamma double dot D, the desired one, you can just say, you know, the gamma dot at the current time minus.
You could, but also again, keep in mind that that's nice. In a continuous system, that would give me better asymptotic tracking that we can prove. We had a negative definite Lyapunov function. But the problem is if you're updating very fast, so here's my current time step, here's the next, and at this rate, my desired rates was here, and then desired rates are here. What's going to happen is it's going to get you there and hold you at that desired rate. That's the gamma minus gamma D, because gamma D doesn't get updated again until here. But if gamma D figured out, look, from here to here, you would have roughly this slope. That's the slope you should be on. While that one feedback term is trying to hold this steady, the other one is trying to push you away. But you can, if you backed off on the gains, you could make it kind of that gamma D dominate with some stuff and then get there a little cleaner. So there's ways, but you have to be really, it's a balance between update rates and those gains that you put into that. So, well, you could make it more complicated. You could take your, you could say your gamma D is your, where you are, you know, instead of just saying it's piecewise fixed, you could see what was my desired gamma. Maybe that was down here earlier. In the next time, well, now I'm here, and you could actually do a constant, you know, variation of your desired gamma dot. You see what I mean? So if you're updating faster in between, you could say, well, I know my last gamma D, and this is how far I've gone. Instead of holding it constant, now I'm here at this, or looking forward. Let me do a different plot. Looking forward, you know, if this is my stuff, gamma D dots. So currently I am here, right? And I know my gamma D double dot, which gives me the local slope that you would have. You could just say, look, as time progresses and my next update is here, instead of just holding this gamma D constant, I'm going to linearly vary that until I get the next time step. If I make that blue, so if blue is the next time step, then the next one may not be here because it's not a linear system, right? It might change. Then all of a sudden gamma dot is here and with this slope, and now you provided these, you know, if it's sampling quicker. And that would try to, the actual response here would, you know, try to lock in on this and then kind of do this, you know, and vary. And that will be smoother. You wouldn't have to have quite the stair-step stuff. So you can see lots of different ways. It depends on the sampling, how precise, because just going to really quick sampling periods and you're giving it a desired one that only gets updated once a second, you're going to get like that stepper motor response where if you hear those things, it's like, because you're literally just moving a tenth of a second, holding it, then slamming it to the next tenth of a second and holding it, right? And that would happen with these things too. Or you can back off on the gains and let that smooth it out naturally. So there's tons of tips and tricks that people do just to get a decent servo. Does that help? Yeah. Okay. So yeah, so there's different ways you can interpret that. But those are the gains I was talking about with the servo, right? That's where you want to put in. The key is though, put your when you're just testing your servo, make your reference act in a reasonable way. That means on the order of half a minute to a minute sine waves. Really slow, benign. Make sure it tracks those reasonably well. And you just put in a sine wave and then you numerically differentiate it. I know there's an analytic answer, but just test your numerical code. Because then later on, instead of gamma D being prescribed, you just get it from that Q eta dot equal to minus LR projection. And that comes in. And then you're ready to go. Okay? Yeah, because this code, once you get past the dynamics, the rest of it can fall together pretty quickly. There's not that much coding to do these inner levels.